Tonight, we are going to step inside one of the most distant objects ever observed by human astronomy and find out what is hidden there. For decades, the first galaxies were a theoretical construct rather than an observed reality. We knew they had to exist. The standard cosmological model required them. The cosmic microwave background measurements implied them. The chemical evolution of the universe demanded them. But we could not see them. They were too distant, too faint, too redshifted into the infrared for any telescope to resolve. The first galaxies were, for most of the history of cosmology, a place we could write equations about, but could not actually visit. That changed in 2022. The James Webb Space Telescope launched on Christmas Day of 2021 and, brought online over the following months, opened its eyes on a sky that no previous instrument could properly see. Within months of its first science observations, it had begun returning images of galaxies at redshifts well above 10, in some cases above 14, corresponding to cosmic times less than 300 million years after the Big Bang. The first galaxies, for the first time in human history, became directly observable. Tonight, we're going to walk into what those observations have revealed, slowly, and find out what is actually inside the first galaxies. The answer turns out to be far stranger than the textbook narrative had prepared us for. The first galaxies contain things they should not contain yet. They are made of components that the standard timeline did not allow time to produce. They are, in their own quiet way, one of the most empirically rich windows into the deep early universe that astronomy has ever opened. Before we get started, sit with what is at stake here. The first galaxies sit at the boundary between the dark ages of the cosmos and the structured universe we live in today. Before them, the cosmos was a featureless plasma of hydrogen and helium gas, illuminated only by the gradually cooling glow of the cosmic microwave background. After them, the cosmos became the textured cosmic web of stars, galaxies, planets, and eventually biology that we observe today. Whatever happened inside the first galaxies determined what kind of cosmos would emerge from that boundary. They are, in the strictest sense, the engines that built the cosmic structure that contains you tonight. Tonight, we're going to walk through 5 specific things that the James Webb data has revealed inside the first galaxies. Each one is a separate empirical surprise. Each one has implications for the broader picture of cosmic structure formation. Each one has its own technical content that deserves to be examined carefully. The 5 things are these. The first thing is population 3 stars. These are the very first generation of stars to ignite in cosmic history. They formed from pure primordial gas, with no heavy elements at all, only hydrogen and helium and trace amounts of lithium. The standard theoretical models predict that they were enormously massive, hundreds of times the mass of the Sun, burning at temperatures and luminosities unlike anything we observe in modern stars. They were also extraordinarily short-lived, blazing across the early cosmos for only a few million years each before exploding as the first supernovae. Whether James Webb has actually detected population 3 stars directly remains contested, but the spectral signatures observed in the first galaxies are pushing the question hard. The second thing is the seeds of the supermassive black holes that occupy the centers of those galaxies. The first galaxies, against every standard expectation, contain supermassive black holes far too early in cosmic history. The masses are too large to have been produced by the gradual accretion of small stellar mass black holes. The seeds for these supermassive monsters had to be something else. The leading candidates include direct collapse black holes, primordial black holes formed in the very early universe, and various exotic alternatives. James Webb is now constraining which of these mechanisms actually produced the seeds we observe. The third thing is the first heavy elements. The standard timeline allowed almost no time for the first generations of stars to forge heavy elements and scatter them into the surrounding gas. The first galaxies observed at cosmic times less than 300 million years after the Big Bang should have been almost entirely hydrogen and helium with only trace amounts of other elements. The James Webb spectra show carbon, nitrogen, oxygen, and sometimes heavier elements in galaxies that the textbook said should not have had time to produce them. The chemical enrichment of the early universe happened, by every available measurement, faster than the standard models predicted. The fourth thing is dust, cosmic dust, the small solid grains of carbon, silicates, and other heavy elements that fill the modern interstellar medium, was not supposed to exist yet in the first galaxies. Dust forms in the slow cooling outflows of evolved stars and in the ejecta of supernovae. Producing substantial dust requires time. The first galaxies observed at the cosmic dawn should have been essentially dust-free. The James Webb observations show that they are not. Some of the first galaxies contain dust masses comparable to those of much later galaxies, raising serious questions about how the dust was assembled so quickly. The fifth thing is the dark matter halos that hold the entire structure together. The first galaxies, like all galaxies, are embedded in much larger halos of dark matter. The structure and properties of these halos determine how gas accumulates at the center and how stars are able to form. The James Webb observations are providing the first detailed constraints on the dark matter halo structure of the cosmic dawn era. The constraints have implications for the broader question of what dark matter actually is, with the data potentially distinguishing between different candidate dark matter models. 5 things. 5 hidden components revealed in the first galaxies by James Webb. By the end of tonight, you will have walked slowly through each one, with enough detail to feel the weight of what is being revealed and enough perspective to see why the discoveries have substantial implications for the broader picture of cosmic structure. Pattern interrupt. The tone of tonight should not be alarm. The discoveries are reshaping the standard cosmological picture in productive ways, not breaking it. The standard frameworks were always known to be incomplete at the cosmic dawn era. James Webb is filling in the picture with surprises that the broader theoretical community is actively incorporating into refined models. What feels from one angle like a series of empirical shocks looks from another angle like the natural process of a frontier becoming directly observable for the first time. Now, let's begin with the first thing, population 3 stars, and what we have managed to learn about them despite never having directly observed a single one with confidence. The first stars in the cosmos formed from primordial gas, the hydrogen and helium that emerged from the early universe after Big Bang nucleosynthesis. The gas, in the moments before the first stars ignited, was almost entirely composed of these two elements, with about 75% hydrogen and 25% helium by mass. Trace amounts of lithium and beryllium also existed, but in quantities so small that they did not substantially affect the physics of star formation. The crucial absence was of heavier elements: carbon, nitrogen, oxygen, silicon, iron, all the elements that modern stars rely on for cooling their natal gas clouds, simply did not exist. This absence had profound consequences for how the first stars could form. Modern stars form from gas clouds that cool through a complex network of atomic and molecular processes, with heavy elements playing a crucial role in radiating away the heat released by gravitational compression. As the gas cloud collapses under its own gravity, the temperature increases. If the gas can cool efficiently, it continues to collapse to higher densities until thermonuclear fusion ignites and a star is born. If the gas cannot cool efficiently, it stops collapsing at lower densities and either does not form a star at all or forms a much more massive object than would otherwise be possible. By the end of tonight, you're going to understand that the primordial gas, lacking heavy elements, was a much less efficient coolant than modern interstellar gas. The dominant cooling mechanism available to it was molecular hydrogen, which formed in small quantities through reactions involving free electrons. Molecular hydrogen cooling is much less efficient than the cooling provided by heavy elements in modern star-forming regions. The result, in the standard models, is that the first stars formed from gas that could only cool to relatively high temperatures, on the order of a few hundred Kelvin, much higher than the temperatures of modern star-forming gas, which can cool to 10 Kelvin or below. The high cooling temperature meant that the first gas clouds collapsed only as far as gravity could overcome the thermal pressure. The critical mass at which gravity wins, called the Jeans mass, scales with temperature in a specific way. For the primordial gas, the Jeans mass was much higher than for modern gas. The resulting first stars were therefore predicted to be much more massive than modern stars, with characteristic masses in the range of 30 to several hundred solar masses, potentially extending to 1,000 solar masses or more in extreme cases. These massive first stars were dramatically different from modern stars in several important ways. They were much more luminous by factors of tens of thousands or more. They burned through their nuclear fuel much faster, with lifetimes of only a few million years, rather than the billions of years that characterize modern sun-like stars. They produced enormous quantities of ionizing ultraviolet radiation, which began the process of reionizing the surrounding intergalactic medium. And they ended their brief lives in extraordinary supernova explosions, scattering the first generation of heavy elements into the surrounding gas. Pattern interrupt. None of the population 3 stars individual to any cosmic location has ever been directly observed. The stars were short-lived enough that they all died billions of years ago. The supernovae that ended their lives are similarly long gone. What we observe today is not the stars themselves, but their indirect signatures encoded in the chemical composition of the galaxies that contain their descendants and in the diffuse properties of the early universe. The search for direct signatures of population 3 stars has been one of the persistent themes of high redshift astronomy for the past 20 years. Several specific spectral features have been proposed as indicators. The most distinctive is the helium-2 emission line at 1640 angstroms, which is produced in the extreme ultraviolet output of very hot stars. Population 3 stars, with their high surface temperatures, would produce strong helium-2 emission. Modern stars, with their cooler surfaces and atmospheres affected by heavy elements, produce much weaker helium-2 emission. The helium-2 signature is, in principle, a clean discriminator. The detection of helium-2 emission in the first galaxies has been a focus of considerable observational effort. Some early James Webb observations have reported tentative detections of helium-2 in galaxies at very high redshift. The detections, however, have generally been at modest signal-to-noise ratios and have not yet been independently confirmed. The community treats them as suggestive, but not yet definitive evidence of population 3 stars in those specific galaxies. The work is ongoing. No one expects, on first thinking about population 3 stars, that the very first stellar generation in cosmic history would have remained essentially invisible to direct observation despite decades of dedicated effort. No one predicts that the empirical search for population 3 stars would, after all this time, still be in the suggestive but not confirmed stage. Absolutely no one anticipates the way the population 3 question has become one of the more persistent open puzzles in modern observational cosmology. What we do know about population 3 stars comes primarily from indirect evidence. The chemical composition of the second generation of stars, called population 2 stars, contains specific patterns that imply the existence of a prior generation of very massive stars whose supernovae produce the observed elemental abundances. The patterns include specific ratios of elements like calcium to iron and silicon to iron that are difficult to produce except in the explosions of very massive stars. The population 2 abundance patterns are, in this sense, the fossil record of the population 3 stars that preceded them. Tonight, we're going to spend a longer pass on the theoretical history of population 3 star research, because the topic has a rich intellectual development, and the search for these objects has shaped much of high redshift astronomy for the past 2 decades. The theoretical study of population 3 stars began in earnest in the late 1990s. Several groups, including Volker Bromm at the Harvard-Smithsonian Center for Astrophysics, Tom Abel at the National Center for Supercomputing Applications, and Naoki Yoshida at the University of Tokyo, began performing detailed numerical simulations of how the first stars would form in primordial gas. The simulations used the best available understanding of gas dynamics, molecular hydrogen chemistry, and cosmological structure formation to predict the conditions under which the first stars would ignite. The results were striking. The first stars in these simulations formed almost exclusively in the densest gravitational wells of the early universe, in dark matter halos with masses of approximately 1 million solar masses. The gas in these halos cooled through molecular hydrogen formation and reached densities sufficient for gravitational collapse. The collapse, lacking the efficient cooling provided by heavy elements in modern star-forming regions, proceeded to relatively high temperatures before fragmentation, producing very massive central objects. The specific mass spectrum of the first stars has been a subject of substantial theoretical work. The early simulations by Bromm and Abel and others suggested that the first stars were typically very massive, with characteristic masses in the range of 100 to several hundred solar masses. Subsequent simulations using improved numerical techniques and including more detailed physics have refined the picture. The current consensus is that the first stars were typically massive, but with a distribution of masses extending from perhaps 10 solar masses to several hundred, with some scenarios allowing extremely massive stars in the range of 1,000 solar masses or more. By the end of tonight, you're going to understand that the search for direct signatures of population 3 stars has been a persistent theme of high redshift astronomy for the past 2 decades. Several different signatures have been proposed as discriminators. Before we get started, sit with what follows. The most distinctive signature is the helium-2 emission line at 1640 angstroms in the rest frame, which is produced by the extreme ultraviolet output of very hot stars. Population 3 stars, with their high surface temperatures and absence of metal line absorption in their atmospheres, would produce strong helium-2 emission. Modern stars, with their cooler surfaces and metal-rich atmospheres, produce much weaker helium-2 emission. The helium-2 signature is therefore, in principle, a clean indicator of population 3 activity. Pattern interrupt. The detection of helium-2 emission in the most distant galaxies has been a focus of considerable observational effort. Searches with the Keck telescopes, the Very Large Telescope in Chile, and previously with Hubble have looked for the signature in various high redshift galaxies. Some tentative detections have been reported. None has been definitively confirmed. Now, let's begin to think about this. The James Webb observations have substantially advanced this search. The NIR SPEC instrument has the spectral resolution and sensitivity needed to detect helium-2 emission in high redshift galaxies if it is present at substantial levels. Several reported tentative detections have appeared in the literature since 2023. The galaxy GNZ11, which we have discussed in other contexts, has been examined in detail for possible helium-2 emission. The current results are suggestive, but not yet definitive. The work continues. Another proposed signature involves the specific spectral shape of the stellar continuum. Population 3 stars with their pure hydrogen-helium composition would produce continuum spectra with specific properties that distinguish them from modern stars. The observational program to look for these continuum properties is ongoing. A third proposed signature involves the specific nucleosynthetic patterns left in the second-generation stars formed from gas enriched by population 3 supernovae. The chemical abundance patterns of the most metal-poor stars observed in the Milky Way halo contain specific features that imply the existence of a prior generation of very massive stars producing characteristic element ratios. The patterns are observed. The interpretation in terms of population 3 nucleosynthesis is, in the broad outline, broadly accepted by the community. No one expects, on first thinking about population 3 stars, that the very first stellar generation in cosmic history would have remained essentially invisible to direct observation despite the best efforts of multiple generations of astronomers. No one predicts that the empirical search for population 3 stars would, after 20 years of dedicated work, still be in the tentative and suggestive stage. Absolutely no one anticipates the way the question of when and where the first stars actually ignited remains one of the open questions in observational cosmology. Walk with me through one specific theoretical development that has shaped the modern understanding. The standard early simulations had population 3 stars forming primarily in isolated halos, with each halo producing perhaps one or a few stars before the radiation feedback shut down further star formation. More recent simulations, including work by Stacey and Brom and by others, have shown that the picture is more complex. Population 3 star formation may have been more clustered, with multiple stars forming together in some halos. The clustering affects the subsequent chemical enrichment patterns and the observable signatures. The work has continued to refine the predictions for when and where population 3 stars should have formed. The current best estimates suggest that the first population 3 stars ignited at cosmic times of perhaps 100 to 150 million years after the Big Bang, with the bulk of population 3 activity occurring between perhaps 150 and 400 million years. The activity declined as the cosmos became chemically enriched with the metallicity reaching levels at which population 3 star formation became impossible at progressively later cosmic times in progressively more enriched regions of the universe. By the end of tonight, you're going to understand that this timeline places population 3 activity exactly in the cosmic epochs that James Webb is now directly observing. The first galaxies that James Webb is identifying at redshifts above 10 correspond to cosmic times when population 3 star formation was actively ongoing in at least some regions of the universe. The probability of detecting population 3 signatures in these galaxies is therefore, in principle, substantial. The empirical work continues with the field expecting that a definitive population 3 detection may emerge over the next several years. Hold this image. The first stars in the cosmos remain, as of this moment, just out of reach of direct observation. Their existence is inferred from indirect evidence and from theoretical reasoning. Their specific properties remain subject to active research. The James Webb observations are pushing the search closer than it has ever been, with the detection of definitive population 3 signatures in the first galaxies being one of the more important pending discoveries in modern observational cosmology. By the end of tonight, you're going to understand that the first thing hidden inside the first galaxies, the population 3 stellar population that produced the chemical building blocks of everything else, remains substantially mysterious despite intensive work. Some of the first galaxies almost certainly contain or contained population 3 stars during their early evolution. The specific signatures of those stars are being looked for with great care. The work has produced suggestive results but no definitive confirmations. The puzzle is one of the more interesting empirical questions in modern high redshift astronomy, and the next several years of James Webb observations may finally settle it. The second thing hidden inside the first galaxies is the seed of every supermassive black hole that now sits at the center of a mature galaxy. Tonight, we're going to walk into this carefully, because the early supermassive black hole puzzle is, in some ways, the most empirically dramatic feature of what the James Webb observations have revealed. The basic situation is this: every large galaxy in the modern universe contains a supermassive black hole at its center. The Milky Way has Sagittarius A star with a mass of approximately 4 million solar masses. The Andromeda Galaxy has a central black hole of approximately 100 million solar masses. Larger galaxies have larger central black holes, with the most massive examples in the centers of giant elliptical galaxies exceeding 10 billion solar masses. The relationship between black hole mass and galaxy mass, called the M-sigma relation, is one of the most striking empirical regularities in modern astrophysics. The question is, how those supermassive black holes got there. The standard story before the James Webb data was that they grew slowly over cosmic time from smaller seed black holes. The seeds were thought to be ordinary stellar mass black holes formed from the deaths of massive stars. These stellar mass seeds, with initial masses of perhaps 10 to 100 solar masses, accreted matter from the surrounding gas over billions of years, gradually growing to the supermassive scale we observe today. The growth process had specific physical limits. The Eddington limit, named after Arthur Eddington, sets the maximum rate at which a black hole can accrete matter under standard conditions. At the Eddington limit, a black hole's mass doubles in approximately 50 million years. To grow from a stellar mass seed of 100 solar masses to a supermassive black hole of 1 million solar masses requires the mass to double approximately 14 times, taking about 700 million years of continuous Eddington-limited accretion. By the end of tonight, you're going to understand why this matters. The James Webb observations have detected supermassive black holes at cosmic times less than 700 million years after the Big Bang. In some cases, the cosmic time at observation is less than 400 million years. The black holes simply have not had time to grow from stellar mass seeds at the standard accretion rate. The math, taken at face value, does not work. Pattern interrupt. Several proposals have been advanced to address this puzzle. None of them is yet fully accepted, but each one represents a serious attempt to explain how supermassive black holes could appear so early in cosmic history. We will walk through each of them. The first proposal is super-Eddington accretion. The Eddington limit, while it is a standard upper limit on accretion rates, can be exceeded under certain conditions. If the geometry of the accreting gas allows radiation to escape through certain channels while matter continues to fall in through others, the effective accretion rate can be much higher than the Eddington value. Recent theoretical work has shown that super-Eddington accretion phases, lasting perhaps a few million years each, can substantially accelerate the growth of black holes in the early universe. If super-Eddington accretion was common in the cosmic dawn era, the standard timescale calculation needs substantial revision. The second proposal is direct collapse black holes. Instead of starting with a stellar mass seed and growing through accretion, the proposal suggests that some early black holes form directly from the collapse of massive gas clouds without ever passing through a stellar phase. The resulting black holes would be much more massive than stellar mass seeds, with initial masses of tens of thousands to hundreds of thousands of solar masses. These intermediate mass seeds would then need to grow by only a few factors of 2 to reach supermassive scale, which is much easier to accomplish within the available cosmic time. The conditions required for direct collapse are demanding. The gas cloud must be massive enough to produce a substantial seed, but it must avoid fragmenting into many small clumps that would form ordinary stars. The standard conditions involve specific requirements on the radiation environment and the metallicity of the gas. The radiation must be sufficient to suppress molecular hydrogen formation, preventing efficient cooling and fragmentation. The metallicity must be very low because heavy elements would also provide cooling channels that lead to fragmentation. These conditions are rare but not impossible in the very early universe. The third proposal is primordial black holes. These are black holes that may have formed in the very early universe within the first fraction of a second after the Big Bang from extreme density fluctuations in the primordial plasma. The fluctuations would have had to be much larger than the average fluctuations we observe in the cosmic microwave background, but specific mechanisms in the early universe could have produced them. Primordial black holes, if they exist, could span a wide range of masses, from microscopic to many solar masses. Some scenarios produce primordial black holes in the intermediate mass range that could serve as ideal seeds for the supermassive black holes observed at high redshift. By the end of tonight, you're going to understand that the three proposals are not mutually exclusive. The actual population of early supermassive black holes may have been produced by a combination of all three. Some may have formed from direct collapse seeds. Some may have formed from primordial black hole seeds. Some may have grown from stellar mass seeds through prolonged super-Eddington accretion phases. The relative importance of the three mechanisms is currently being investigated through both theoretical work and ongoing observations. The most striking specific case in the James Webb data is the galaxy GNZ11, originally discovered by Hubble at a redshift of approximately 10.6, corresponding to a cosmic time of about 420 million years after the Big Bang. The James Webb spectroscopy of GNZ11 has revealed clear evidence of an active galactic nucleus powered by a supermassive black hole of approximately 1 to 2 million solar masses. The black hole is, by every available calculation, too massive for the available cosmic time under standard assumptions. No one expects, on first thinking about cosmic black hole assembly, that the question of how supermassive black holes got their start would still be substantially unresolved after decades of theoretical work. No one predicts that the James Webb data would so dramatically sharpen the puzzle by detecting supermassive black holes at even earlier cosmic times than the previous Hubble observations had suggested. Absolutely no one anticipates the way the early supermassive black hole question has become one of the more empirically dramatic features of modern cosmology. The implications for the broader picture of galaxy evolution are substantial. The relationship between black holes and their host galaxies, which we see in the modern universe through the M-sigma relation, must have been established somehow during the cosmic dawn era. If supermassive black holes were already in place when the first galaxies were forming, then the black holes may have played a significant role in regulating the assembly of those galaxies. Feedback from the active galactic nuclei powered by the seed black holes could have heated and dispersed gas, suppressing star formation or redirecting it in specific ways. The early supermassive black holes may have been not just incidental features of early galaxy centers, but active participants in shaping how the galaxies grew. Walk with me through what this implies for what is hidden inside the first galaxies. The standard picture before the James Webb data had the centers of the first galaxies as relatively quiet regions, with stellar mass black holes only just beginning to accrete matter. Expectation, the standard picture. Reality, the revised picture, based on the James Webb observations, has the centers of the first galaxies as already substantially active, with seed black holes of intermediate mass already in place and already powering the assembly of the surrounding stellar populations. The centers of the first galaxies are, in this revised picture, much more dynamic than the standard story suggested. Hold this image. The supermassive black holes that occupy the centers of every large galaxy in the modern universe got their start in the first galaxies. The seed black holes were either direct, collapse remnants of primordial gas clouds, or primordial black holes from the very early universe, or stellar mass black holes that grew rapidly through super-Eddington accretion, or some combination of all three. The James Webb data is, in this sense, providing direct empirical input to questions about black hole formation that have been theoretical for decades. By the end of tonight, you're going to understand that the second thing hidden inside the first galaxies is therefore one of the most important questions in modern cosmology. The seeds of every modern supermassive black hole are there, in the first galaxies in some form. The James Webb observations are slowly identifying which form. The work over the next decade will likely settle the question of how the cosmic supermassive black hole population actually originated. Before we walk into the third thing, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. We should pause to acknowledge why this kind of careful walk through the deep interior of the first galaxies exists at all. Tonight, we're going to walk through the specific physics of direct collapse black hole formation because the mechanism is one of the more striking theoretical proposals in modern astrophysics, and the conditions required for it to operate are worth understanding in some detail. The basic challenge that direct collapse addresses is the production of black holes with intermediate masses in the range of 10,000 to 100,000 solar masses in the early universe. These intermediate mass black holes are much larger than the stellar mass black holes that form from the deaths of individual massive stars. They are much smaller than the supermassive black holes observed at the centers of mature galaxies. Their intermediate mass makes them ideal seeds for the supermassive black holes that we observe at the centers of the first galaxies, because they require much less subsequent accretion growth to reach supermassive scale than stellar mass seeds would require. The direct collapse mechanism proposes that some intermediate mass black holes form directly from the collapse of massive gas clouds in the early universe without ever passing through a stellar phase. The mechanism requires very specific conditions to operate. The gas cloud must be massive, with a total mass of at least several million solar masses. The cloud must avoid fragmenting into many smaller clumps that would form ordinary stars. The cloud must be able to lose angular momentum quickly enough that gravitational collapse can proceed to high densities. The collapse must produce a single, massive, central object, rather than a distributed star cluster. By the end of tonight, you're going to understand that the conditions required for direct collapse have been worked out in considerable detail. The most important condition is the suppression of molecular hydrogen cooling. Molecular hydrogen, the dominant coolant in primordial gas, is destroyed by ultraviolet radiation in the so-called Lyman-Werner band, which corresponds to specific wavelengths in the far ultraviolet. If a primordial gas cloud is exposed to sufficient Lyman-Werner radiation from neighboring stellar populations, the molecular hydrogen is destroyed, the cooling is suppressed, the gas cannot fragment efficiently, and the collapse may proceed monolithically. The Lyman-Werner radiation field required to suppress molecular hydrogen cooling has been calculated by theoretical work. The required radiation intensity is substantial, but not impossibly high. The intensity can be reached in the vicinity of neighboring galaxies undergoing active star formation, particularly if those neighboring galaxies are sufficiently massive and sufficiently close to the direct collapse candidate. Pattern interrupt. The specific scenarios proposed for direct collapse typically involve two halos in close proximity. One halo undergoes early star formation, producing the Lyman-Werner radiation field. The other halo, located close enough to receive the radiation, but not so close that it has already begun its own star formation, becomes the direct collapse site. The collapsing gas in the second halo, lacking molecular hydrogen cooling because of the radiation field, falls to high densities essentially monolithically, producing a single massive central object. The end stage of direct collapse is the formation of what is called a quasi-star or a supermassive star. The supermassive star is an enormous gas cloud, possibly with internal hydrogen fusion in its core, that lasts for only a few million years before collapsing to form a black hole. The black hole inherits the mass of the supermassive star, which can be anywhere from 10,000 to several 100,000 solar masses, depending on the specific conditions. The resulting intermediate mass black hole is the direct collapse seed. The direct collapse mechanism has been the subject of substantial theoretical work over the past 2 decades. The leading researchers include Marta Volonteri at the Institut d'Astrophysique de Paris, Mitchell Bagelman at the University of Colorado, and Zoltan Hyman at Columbia University. The numerical simulations of direct collapse have become increasingly sophisticated, with the most recent simulations being able to follow the collapse from cosmological initial conditions through to the formation of the central black hole. The empirical status of direct collapse is mixed. The mechanism is theoretically viable. The conditions required for it to operate are plausibly met in the early universe at the rates needed to produce the observed population of supermassive black hole seeds. But no individual direct collapse event has ever been directly observed. The mechanism is, in this sense, theoretically well motivated, but empirically unconfirmed. The James Webb observations are providing the first opportunity to constrain direct collapse empirically. If direct collapse is common in the early universe, then supermassive black hole seeds with intermediate masses should be detectable in some of the most distant galaxies. The detection of such seeds through their characteristic spectral signatures from active accretion would provide empirical evidence for the mechanism. The James Webb spectroscopy of high redshift galaxies has begun to identify candidate intermediate mass black holes, though the identifications are still tentative. No one expects, on first thinking about black hole formation, that the seeds of the supermassive black holes at the centers of every modern galaxy might have come from such an exotic mechanism. No one predicts that the direct collapse of gas clouds in the very early universe could produce intermediate mass black holes that then grew through subsequent accretion. Absolutely no one anticipates the way the direct collapse mechanism has, despite its lack of direct empirical confirmation, become one of the leading candidates for the origin of the supermassive black hole population. Walk with me through the implications for what is hidden inside the first galaxies. The supermassive black holes that occupy the centers of the first galaxies must have formed somehow. The direct collapse mechanism is one of the leading candidates. If direct collapse is correct, then the centers of the first galaxies contain not just supermassive black holes, but specific kinds of supermassive black holes with characteristic mass distributions and characteristic formation histories. The James Webb observations are providing data that can, in principle, distinguish between direct collapse and the alternative mechanisms. By the end of tonight, you're going to understand that the direct collapse mechanism is one of the more dramatic theoretical proposals in modern astrophysics. The mechanism requires specific physical conditions to operate. The conditions are plausibly met in the early universe but have not been directly confirmed. The James Webb observations are providing the first opportunity to test the mechanism empirically. The results, when they come, will substantially advance our understanding of how the supermassive black hole population that dominates the centers of modern galaxies originated. Before we continue, why this channel exists. If you have made it this far into a careful examination of what is hidden inside the first galaxies, you are not the casual viewer the platform expects. You are the person for whom this channel was built, long-form cosmology, told at the pace of sleep, with enough technical detail to actually feel the weight of the discoveries, rather than just the headline summaries, is not what the algorithm rewards. It is what we make anyway, because we believe the cosmos is more interesting when the questions are developed slowly rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about reality. If you have already subscribed, thank you, truly. If this is your first long-form night with the channel, welcome. The queue contains many more nights like this one. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there as well. The audio versions are tuned for the same purpose, the same pace. the same care. Now, let us return to the data. The third thing is waiting. The third thing hidden inside the first galaxies is the first chemical inventory of the cosmos. The standard timeline did not allow much time for the first stars to forge heavy elements and scatter them into the surrounding gas. The James Webb observations show that the first galaxies, against this expectation, were already substantially chemically enriched by the cosmic times at which we now observe them. Tonight, we're going to walk into the chemistry of the early universe slowly, because the timing of cosmic chemical enrichment is one of the most informative empirical results to emerge from James Webb so far. The basic picture is this. The cosmos after Big Bang nucleosynthesis contained essentially only hydrogen and helium, with trace amounts of lithium and beryllium. No carbon, no nitrogen, no oxygen, no silicon, no iron. The entire periodic table beyond helium did not yet exist in any substantial quantity. The first generation of stars, the population 3 stars we discussed in the first truth, had to produce these elements through nuclear fusion in their cores and then scatter them into the surrounding gas through their supernova explosions. The standard timeline allowed for this process to proceed gradually over several 100 million years. The first population 3 stars ignited perhaps 100 to 200 million years after the Big Bang. They lived for only a few million years each before dying as supernovae. The supernovae scattered their nuclear fusion products, including the first carbon, oxygen, silicon, and iron, into the surrounding interstellar gas. Subsequent generations of stars formed from this enriched gas, gradually building up the heavy element content of the cosmos over hundreds of millions of years. The first galaxies in the standard picture should have been observed in this period of gradual chemical buildup. The earliest first galaxies should have been essentially pure hydrogen and helium, with only the smallest traces of the heavy elements just beginning to be produced by their first stellar generations. By cosmic times of 300 or 400 million years after the Big Bang, the first galaxies should have shown modest chemical enrichment, with heavy element abundances perhaps a few % of the modern solar value. Higher abundances would have required either earlier or more rapid chemical enrichment than the standard picture allowed. By the end of tonight, you're going to understand that the James Webb observations have shown that the actual chemical enrichment of the first galaxies is more advanced than this. The spectra of galaxies at redshifts above 10 consistently show emission lines from carbon, nitrogen, oxygen, and sometimes heavier elements. The abundance levels, while still lower than modern values, are substantially higher than the simplest models predicted for the relevant cosmic times. The cosmos was, by every available measurement, chemically enriching itself faster than the textbook allowed. Pattern interrupt. The specific observations have come from spectroscopy of the most distant galaxies. The James Webb NIR-SPEC instrument can disperse the light from a galaxy into a spectrum, revealing the specific wavelengths at which atoms and ions in the galaxy are emitting or absorbing radiation. The wavelengths correspond to specific quantum transitions in specific elements. By measuring the relative strengths of different spectral lines, astronomers can determine the chemical composition of the gas producing the spectrum. The most striking specific result has involved nitrogen. The galaxy GNZ11, which we discussed earlier in the context of supermassive black holes, also shows extraordinary spectroscopic evidence for nitrogen enrichment. The nitrogen abundance in GNZ11, derived from the strength of the nitrogen emission lines, is substantially higher than would be expected for a galaxy at its cosmic time. The nitrogen, in particular, is overabundant relative to oxygen by factors that are difficult to explain through the standard chemical evolution processes. The puzzle of nitrogen in GNZ11 has prompted substantial theoretical work. Several explanations have been proposed. One possibility is that the galaxy contains a particularly rapid generation of star formation, with the nitrogen produced through specific nucleosynthetic channels in massive stars. Another possibility is that the nitrogen has been preferentially enriched by the central supermassive black hole through specific accretion-related processes. A third possibility involves the contribution of more exotic stellar populations, including very massive stars in the range of hundreds of thousands of solar masses that could produce specific nucleosynthetic patterns. By the end of tonight, you're going to understand that none of these explanations has been definitively confirmed. The nitrogen puzzle in GNZ11 remains an active area of research. Whatever the correct explanation turns out to be, the observation shows that the chemical evolution of the first galaxies was substantially more rapid and more complex than the standard models allowed. Similar patterns have been observed in other high redshift galaxies. The Sears survey, the JWST survey, and the Cosmos Webb survey have all reported evidence for substantial chemical enrichment in galaxies at the highest redshifts, where any spectroscopy has been obtained. The pattern is consistent across multiple surveys. The first galaxies were chemically enriched at levels that, for their cosmic times, exceeded the standard predictions. The implications for the broader picture of cosmic chemical evolution are substantial. The standard models had cosmic chemistry building up gradually over many generations of stars. The James Webb data suggests that the build-up was much faster, with the first generations of stars producing more chemical enrichment per unit of stellar mass than the simple models assumed. The reasons may involve the specific properties of population 3 stars, including their high masses and their distinctive nucleosynthetic patterns. The reasons may also involve faster recycling of gas between stellar generations than the standard models allowed. No one expects, on first thinking about cosmic chemical evolution, that the first galaxies would already be substantially enriched in heavy elements at the cosmic times when James Webb is observing them. No one predicts that the chemical build-up timescale would need to be compressed in the same way that the structural build-up timescale needs to be compressed. Absolutely no one anticipates the way the chemistry of the early universe has become one of the more empirically active questions in current cosmology. Walk with me through one specific implication for the question of what is hidden inside the first galaxies. The chemical inventory of the first galaxies observed by James Webb includes substantial amounts of carbon, nitrogen, oxygen, silicon, and other heavy elements. These elements were forged in the cores of the first stars and scattered by the first supernovae. The chemistry tells us specifically what those first stellar generations did. The patterns of relative abundances encode the masses, the rotation rates, the explosion mechanisms, and the metallicities of the stars that produced them. Step back, and you can see that this means the James Webb spectroscopy of the first galaxies is essentially a forensic analysis of the first stellar generations. Even though we cannot directly observe population 3 stars themselves, we can read their fingerprints in the chemical composition of the galaxies that contain them. The forensic analysis is in its early stages, but it is producing specific results. The first stars, by every available measurement, were nucleosynthetically more interesting than the standard models had assumed. Tonight, we're going to walk through the specific nucleosynthesis of the first supernovae, because the details of how the first heavy elements were produced are one of the more concrete connections between the deep early universe and the chemistry that allows your existence. The basic story is this: the population 3 stars, the very first generation of stars in cosmic history, were generally very massive. The standard estimates put their characteristic masses in the range of 30 to several hundred solar masses, with some scenarios allowing extreme cases up to 1,000 solar masses or more. The high masses had specific implications for how these stars lived and died. Massive stars, regardless of their formation epoch, burn through their nuclear fuel much faster than smaller stars. A solar mass star, like our Sun, lives for approximately 10 billion years on the main sequence, burning hydrogen into helium in its core. A massive star of 100 solar masses lives for only a few million years before exhausting its hydrogen supply. The first population 3 stars, with their high masses, therefore lived only briefly on cosmic timescales before evolving toward their final stages. What this leaves us with is that the deaths of massive stars produce specific patterns of heavy elements through nuclear processes that depend sensitively on the stellar mass. The dominant nucleosynthetic mechanisms include hydrostatic burning during the late stellar evolution, explosive nucleosynthesis during the supernova event itself, and various neutron capture processes that produce elements heavier than iron. The hydrostatic burning phases produce a characteristic set of elements through successive nuclear fusion reactions in the stellar core. Hydrogen burns to helium, helium burns to carbon and oxygen, carbon burns to oxygen, neon, magnesium, and silicon. Oxygen burns to silicon, sulfur, argon, and calcium. Silicon burns through a complex network of reactions producing elements up to iron. The successive burning phases happen at progressively higher temperatures in progressively smaller central regions of the star, with each phase lasting a progressively shorter time. Pattern interrupt. The most important products of hydrostatic burning from the perspective of cosmic chemistry are carbon, oxygen, neon, magnesium, silicon, sulfur, and calcium. These elements, sometimes called the alpha elements because they can be built up from helium nuclei through specific nuclear reactions, are produced in characteristic ratios in massive stars. The alpha element ratios are one of the more direct chemical signatures of massive star nucleosynthesis. The explosive nucleosynthesis phase happens during the supernova event itself, when the stellar core collapses and the outer layers are ejected at high velocity. The high temperatures and densities of the explosive shock produce additional heavy elements through reactions that cannot operate at the lower temperatures of hydrostatic burning. The dominant products of explosive nucleosynthesis include iron and elements in the iron group, including chromium, manganese, cobalt, and nickel. The specific yields depend on the explosion mechanism and the details of the shock propagation through the stellar envelope. The neutron capture processes produce elements heavier than iron. These processes require free neutrons, which are generated through specific nuclear reactions during late stellar evolution and during the supernova event. The neutron capture can be slow, allowing time for radioactive decays between successive captures, or rapid, with multiple captures occurring before any decay. The slow process produces elements like barium and strontium. The rapid process produces elements like europium, gold, and uranium. The rapid neutron capture process is responsible for approximately half of the elements heavier than iron in the modern universe. The point worth taking away is that the first supernovae produced specific patterns of these various heavy elements. The exact patterns depend on the specific masses and properties of the exploding stars. Very massive stars in the range of 100 to 1,000 solar masses may produce different element ratios than the more moderate masses of 15 to 50 solar masses. The specific patterns produced by population 3 supernovae are predicted by detailed nucleosynthesis calculations and can be compared to the chemical abundance patterns observed in the most metal-poor stars in the Milky Way halo. The comparison has produced specific results. The most metal-poor stars in the Milky Way halo, with iron abundances less than 1/10,000th of solar, contain element ratios that are difficult to produce except through population 3 nucleosynthesis. The carbon-to-iron ratios are unusually high in many of these stars. The alpha element ratios are typically enhanced relative to solar values. The neutron capture element abundances follow specific patterns that imply contributions from particular kinds of supernovae. The overall picture, when analysed in detail, is consistent with the chemical inventory of these stars having been produced primarily by population 3 supernovae, with subsequent generations of star formation adding only small modifications. No one expects, on first thinking about cosmic chemistry, that the abundance patterns of the most metal-poor stars in the modern Milky Way would contain such specific and detailed information about the supernovae of stars that died more than 13 billion years ago. No one predicts that the chemical forensics of population 3 nucleosynthesis would be one of the more productive empirical probes of the first stellar generation. Absolutely no one anticipates the way the chemistry of the first stars has, despite the stars themselves being unobservable, become one of the more empirically rich windows into the cosmic dawn era. The implications for what is hidden inside the first galaxies are direct. The first galaxies contain the chemical products of the first supernovae. The James Webb spectroscopy is now detecting the carbon, nitrogen, oxygen, silicon, and iron in these galaxies. The relative abundances, when analysed carefully, contain information about the specific properties of the first stellar generations that produced them. The chemistry of the first galaxies is, in this sense, a direct probe of the physics of population 3 supernovae. Walk with me through one specific result that has emerged from the James Webb data. The galaxy GNZ 11, observed at a redshift of about 10.6, shows extraordinary nitrogen enrichment relative to oxygen. The ratio of nitrogen to oxygen in GNZ 11 is approximately 10 times higher than the ratio observed in modern galaxies at similar metallicity levels. The high nitrogen abundance has prompted substantial theoretical work to identify the specific nucleosynthetic mechanisms responsible. Several explanations have been proposed. One possibility involves the rapid mixing of nitrogen-rich material from the late stages of stellar evolution into the surrounding gas. Another possibility involves contributions from very massive stars in the range of hundreds of solar masses, which can produce nitrogen through specific channels in their late evolution. A third possibility involves the contribution of nitrogen-rich supernovae from very specific stellar configurations. Each of these explanations has its own implications for the broader picture of cosmic chemistry. Hold this image. The chemistry of the first galaxies observed in detail by James Webb contains specific information about the first stellar generations that produced it. The information is being decoded slowly through the careful comparison of observed abundance patterns with theoretical nucleosynthesis predictions. The early results suggest that the first stars were nucleosynthetically more interesting than the standard models had assumed. The work continues with substantial implications for the broader understanding of how the cosmic chemical inventory came into being. Hold this image. The first galaxies contain, hidden in their gas and stellar populations, the chemical record of every cosmic process that produced the carbon in your cells, the oxygen in your breath, the calcium in your bones, the iron in your blood. The first generations of stars forged these elements, the supernovae scattered them, the interstellar medium of the first galaxies preserved them. The chemical inventory of those galaxies, as the James Webb data is now beginning to reveal, contains the precise chemical history of how everything beyond hydrogen and helium came into being. The chemistry of the first galaxies is, in this sense, one of the most directly informative components hidden inside them. The specific abundance patterns are still being measured, the interpretations are still being developed, but the empirical content is rich and the implications for cosmic chemical evolution are substantial. The cosmos enriched itself faster than the textbook allowed. The chemistry of the first galaxies is the direct evidence for this fact. The fourth thing hidden inside the first galaxies is, in some ways, the most surprising of all. Tonight, we're going to walk into the dust of the early universe because the presence of substantial cosmic dust in the first galaxies at the cosmic times when James Webb is observing them is one of the more empirically dramatic results to emerge from the new data. Cosmic dust is one of the most important components of the modern interstellar medium. It consists of small solid grains, typically nanometers to micrometers in size, made of carbon, silicates, and various other heavy element compounds. The grains form in the slow cooling outflows of evolved stars and in the ejecta of supernovae. They absorb and scatter starlight, dim the visible appearance of distant galaxies, and re-emit the absorbed energy as infrared radiation. The dust is, in this sense, both a feature of the interstellar medium and an indicator of the chemical and physical history of the gas in which it resides. The standard picture of cosmic dust evolution has the grains forming gradually over cosmic time, with the dust budget building up as successive generations of stars produce and release the necessary materials. In the modern universe, the relationship between dust mass and total gas mass in galaxies is well characterized. Mature galaxies have dust-to-gas mass ratios of approximately 1 to 100, with the dust accumulating over billions of years of stellar evolution and supernova activity. What becomes clear is that the first galaxies observed at cosmic times less than 700 million years after the Big Bang should not have had time to produce substantial dust. The standard models predict that the first galaxies should be essentially dust-free, with the dust formation processes only just beginning to operate. The first stellar generations had to live, die, and scatter their products into the interstellar medium before dust could begin to form in significant quantities. The cumulative dust production over the available cosmic time in the standard models should produce only modest dust masses in the first galaxies, perhaps less than 1% of the dust mass observed in mature galaxies. The James Webb observations show that this prediction is wrong. The first galaxies contain dust, substantial dust. Some of the first galaxies observed at the cosmic dawn contain dust masses comparable to those of much later galaxies. The dust is, by every available measurement, there. The standard models cannot easily produce it. Pattern interrupt. The empirical evidence for substantial dust in the first galaxies has come from several different observational approaches. Some galaxies show direct evidence of dust through the reddening of their spectra, with the blue end of the spectrum suppressed relative to the red end in ways that imply absorption by intervening dust. Other galaxies show dust through specific infrared emission features, including the polycyclic aromatic hydrocarbon emission bands that are characteristic of certain types of dust grains. Still, other galaxies show dust through their submillimeter emission, observed by ground-based telescopes like the Atacama Large Millimeter Array and the Submillimeter Array, which detect the thermal radiation from warm dust at much longer wavelengths than James Webb can directly observe. The combination of evidence is robust. Substantial dust has been detected in multiple galaxies at very high redshift. The dust masses, while smaller than those in modern galaxies, are large enough to require substantial production within the limited cosmic time available. The puzzle is real. The mechanisms proposed for producing the early dust fall into several categories. The first category invokes very rapid dust production by population 3 supernovae. If the first generations of stars were as massive as the standard models suggest, their supernovae would have been particularly violent and would have produced substantial amounts of refractory elements that could condense into dust grains in the cooling ejecta. The condensation efficiency in supernova ejecta has been studied theoretically, with estimates suggesting that a substantial fraction of the heavy elements produced in a supernova can end up in dust grains under the right conditions. The second category invokes dust production in the slowly cooling envelopes of post-asymptotic giant branch stars. In the modern universe, much of the cosmic dust budget comes from the slow stellar winds of aging stars in their red giant phase. The standard picture had these stars contributing only modestly in the early universe because the available cosmic time was too short for many stars to have reached the red giant phase. Recent work has suggested that some specific stellar populations may have reached this phase faster than the standard models allowed, contributing more dust than was originally predicted. Notice that the third category invokes more exotic mechanisms, including the formation of dust in the immediate aftermath of the first supernovae through specific high-density condensation processes. Whether these mechanisms can actually operate efficiently enough to produce the observed dust masses is an active question in theoretical astrophysics. The work continues with both observational and theoretical efforts trying to identify the dominant pathway by which the early cosmos produced its first dust. The implications of the early dust are substantial. The dust affects how we observe the first galaxies. Galaxies with substantial dust appear dimmer in the visible and ultraviolet than they would otherwise be, with the absorbed radiation being re-emitted at infrared wavelengths. The James Webb observations are seeing some of the most distant galaxies at infrared wavelengths where their thermal dust emission contributes significantly to the observed brightness. The dust is, in this sense, both a complication for observation and a tracer of physical conditions in the early universe. The dust also affects the physics of star formation in the first galaxies. Dust grains play a crucial role in the cooling of gas in modern star-forming regions. By absorbing the energy released during gravitational collapse and re-emitting it at infrared wavelengths that escape the cloud. Without dust, the cooling efficiency is lower and star formation proceeds differently. The presence of substantial dust in the first galaxies suggests that star formation conditions in those galaxies may have been more similar to modern star formation than the dust-free standard picture allowed. No one expects, on first thinking about the cosmic dust budget, that the first galaxies would already contain substantial dust at the cosmic times when James Webb is observing them. No one predicts that the dust production timescale would need to be compressed in the same way that the timescales for stellar formation and chemical enrichment need to be compressed. Absolutely no one anticipates the way the dust problem has become another concrete example of how the standard models of the early universe need substantial revision. Walk with me through one specific case study. The galaxy designated Cosmos-3 is one of the more striking examples of early dust. Observed at a redshift of approximately 7, corresponding to a cosmic time of about 750 million years after the Big Bang, the galaxy shows substantial dust through both its infrared emission and the reddening of its visible spectrum. The dust mass implied by the observations is approximately 10 million solar masses, which is comparable to the dust masses of much larger and more mature galaxies in the modern universe. For a galaxy at such an early cosmic time, the dust mass is unusually large. Similar results have been obtained for other galaxies in the same general cosmic epoch. The pattern is consistent. Some fraction of the first galaxies contain substantial dust. The pattern is not universal. Other galaxies in the same epoch show much less dust. The empirical picture is one of substantial diversity, with some early galaxies being relatively dust-rich and others being relatively dust-poor. Understanding what determines which galaxies end up with substantial dust and which do not is one of the active questions in current observational astronomy. Tonight, we're going to walk through the specific observations that have revealed substantial dust in the first galaxies, because the dust observations involve a combination of multiple facilities and have been one of the more empirically dramatic results in modern cosmology. The detection of dust in the most distant galaxies relies on observations at multiple wavelengths. The dust grains, when heated by absorbed starlight, re-emit thermal radiation at long wavelengths, primarily in the far infrared and sub-millimeter regions of the spectrum. By the time the radiation has traveled from a distant galaxy to Earth, the cosmic expansion has stretched it to even longer wavelengths. The dust emission from the most distant galaxies is detected by ground-based telescopes operating in the sub-millimeter and millimeter bands. The Atacama Large Millimeter Array, called ALMA, located at 5,000 meters elevation in the Atacama Desert of Chile, has been the workhorse facility for detecting dust in the most distant galaxies. ALMA consists of 66 high-precision antennas operating together as an interferometer, providing sensitivity and spatial resolution that no other facility can match in the sub-millimeter wavelength range. ALMA began full science operations in 2013 and has, over the subsequent decade, transformed our understanding of dust in the early universe. What emerges from this is that the ALMA observations of the first galaxies have produced a series of striking results. The first major result came in 2015, when the galaxy A2390, at a redshift of approximately 7.5, was detected through its dust continuum emission. The dust mass implied by the detection was approximately 10 million solar masses, comparable to the dust masses observed in much more mature galaxies. The detection was an early indication that substantial dust existed in the first galaxies despite the apparent lack of time for it to form. Pattern interrupt. Subsequent observations extended the detection of dust to even more distant galaxies. The galaxy MAX.0416, at a redshift of approximately 9, was detected through ALMA observations in 2020. The galaxy GNZ11, which we have discussed in several other contexts, has been observed by ALMA with results suggesting substantial dust content. The galaxy JWST 14, the current record holder for the most distant confirmed galaxy at a redshift of approximately 14.3 has been targeted by ALMA observations that may detect its dust emission if it is present at substantial levels. The combination of ALMA submillimeter observations and James Webb infrared observations provides a powerful empirical tool for studying dust in the first galaxies. ALMA detects the long wavelength thermal emission from the dust itself. James Webb detects the reddening of the visible spectrum produced by dust absorption plus emission features at shorter wavelengths that indicate the chemical composition of the dust grains. The combination provides a complete picture of the dust properties. The James Webb observations have begun to detect specific spectral features associated with cosmic dust. The polycyclic aromatic hydrocarbon emission features called Page features are characteristic of certain types of dust grains and produce specific emission bands at wavelengths of 3.3, 6.2, 7.7, 8.6, and 11.3 micrometers. The James Webb MIRI instrument can detect these features in galaxies at moderate redshifts, providing direct evidence for the presence of specific dust populations. The PAH features have been detected in some of the most distant galaxies that James Webb can observe. The detections imply not just dust in general, but specific chemical populations of dust that resemble those in modern galaxies. The chemistry of the dust grains, in this sense, was substantially developed by the cosmic times when James Webb is observing the first galaxies. No one expects, on first thinking about the cosmic dust budget, that the first galaxies would already contain substantial dust with chemical compositions similar to those of modern galaxies. No one predicts that the dust production timescale would need to be compressed in the same way that the timescales for stellar formation and chemical enrichment need to be compressed. Absolutely no one anticipates the way the early dust observations have become another concrete example of how the standard models of the early universe need substantial refinement. Walk with me through what this implies for the broader picture of cosmic chemistry. The dust in the first galaxies represents a substantial fraction of the heavy elements that the first generations of stars produced. The dust is not just incidental matter, it is the form in which much of the cosmic carbon and silicon and other heavy elements existed in the early universe. The chemistry of the first galaxies, including their dust budgets, encodes the specific patterns of element production by the first stellar generations. The empirical detection of substantial dust in the first galaxies has prompted substantial theoretical work to identify the dominant production mechanisms. The leading candidates include rapid dust production by population 3 supernovae and dust production in the late stages of evolution of specific stellar populations. Whether either of these mechanisms can actually operate efficiently enough to produce the observed dust masses is an active question. The implications for how we observe the first galaxies are also substantial. Dust absorbs visible and ultraviolet light and re-emits it as infrared radiation. The most distant galaxies observed through the dust they contain appear dimmer in the optical and brighter in the infrared than they would in the absence of dust. The James Webb observations are specifically tuned to the infrared range where the dust-affected radiation is most prominent. The first galaxies are, in this sense, particularly amenable to study with James Webb precisely because of their dust. Hold this image. The dust hidden inside the first galaxies is not a small effect. It is a substantial component of the interstellar medium of those galaxies, with masses comparable to those of much more mature systems and chemical compositions similar to those of modern galactic dust. The dust affects how we observe the first galaxies. The dust encodes the chemistry of the first stellar generations. The dust connects the various puzzles of the cosmic dawn era into a single coherent story of how the early universe became chemically and physically complex. What this picture tells us is that the early dust is one of the more concrete examples of how the standard cosmological picture needs revision. The first galaxies were not the simple dust-free systems that the textbook predicted. They were already chemically and physically rich systems with substantial dust budgets that the standard models cannot easily produce. The implications extend across multiple aspects of early universe cosmology and represent one of the active areas of current research. Hold this image. The first galaxies are not the dust-free systems that the standard models had predicted. They contain, in many cases, substantial cosmic dust, produced by mechanisms that the standard models struggle to identify clearly. The dust affects how we observe them and how they evolved internally. The dust is, in this sense, one of the more concrete examples of how the textbook picture of the early universe needs substantial refinement. What this picture tells us is that the dust hidden inside the first galaxies is not just a footnote in the story of cosmic evolution. It is a substantial empirical surprise that has implications for stellar populations, supernova nucleosynthesis, interstellar medium physics, and the broader chemical evolution of the cosmos. The dust connects the chemistry of the third truth to the structural questions of the second truth and to the dark matter halo questions of the fifth truth that we will come to next. The first galaxies are, in this respect, much richer in their internal physics than the simple models suggested. Tonight, we're going to walk through the specific observations that have revealed substantial dust in the first galaxies, because the dust observations involve a combination of multiple facilities and have been one of the more empirically dramatic results in modern cosmology. The detection of dust in the most distant galaxies relies on observations at multiple wavelengths. The dust grains, when heated by absorbed starlight, re-emit thermal radiation at long wavelengths, primarily in the far infrared and submillimeter regions of the spectrum. By the time the radiation has traveled from a distant galaxy to Earth, the cosmic expansion has stretched it to even longer wavelengths. The dust emission from the most distant galaxies is detected by ground-based telescopes operating in the submillimeter and millimeter bands. The Atacama Large Millimeter Array, called ALMA, located at 5,000 meters elevation in the Atacama Desert of Chile, has been the workhorse facility for detecting dust in the most distant galaxies. ALMA consists of 66 high-precision antennas operating together as an interferometer, providing sensitivity and spatial resolution that no other facility can match in the sub-millimeter wavelength range. ALMA began full science operations in 2013 and has, over the subsequent decade, transformed our understanding of dust in the early universe. What emerges from this is that the ALMA observations of the first galaxies have produced a series of striking results. The first major result came in 2015 when the galaxy A2390, at a redshift of approximately 7.5, was detected through its dust continuum emission. The dust mass implied by the detection was approximately 10 million solar masses, comparable to the dust masses observed in much more mature galaxies. The detection was an early indication that substantial dust existed in the first galaxies despite the apparent lack of time for it to form. Pattern interrupt. Subsequent observations extended the detection of dust to even more distant galaxies. The galaxy MAX.0416, at a redshift of approximately 9 was detected through ALMA observations in 2020. The galaxy GNZ11, which we have discussed in several other contexts, has been observed by ALMA with results suggesting substantial dust content. The galaxy JWST, the current record holder for the most distant confirmed galaxy at a redshift of approximately 14.3, has been targeted by ALMA observations that may detect its dust emission if it is present at substantial levels. The combination of ALMA submillimeter observations and James Webb infrared observations provides a powerful empirical tool for studying dust in the first galaxies. ALMA detects the long wavelength thermal emission from the dust itself. James Webb detects the reddening of the visible spectrum produced by dust absorption, plus emission features at shorter wavelengths that indicate the chemical composition of the dust grains. The combination provides a complete picture of the dust properties. The James Webb observations have begun to detect specific spectral features associated with cosmic dust. The polycyclic aromatic hydrocarbon emission features, called PAH features, are characteristic of certain types of dust grains and produce specific emission bands at wavelengths of 3.3, 6.2, 7.7, 8.6, and 11.3 micrometers. The James Webb MIRI instrument can detect these features in galaxies at moderate redshifts, providing direct evidence for the presence of specific dust populations. The PAH features have been detected in some of the most distant galaxies that James Webb can observe. The detections imply not just dust in general, but specific chemical populations of dust that resemble those in modern galaxies. The chemistry of the dust grains, in this sense, was substantially developed by the cosmic times when James Webb is observing the first galaxies. No one expects, on first thinking about the cosmic dust budget, that the first galaxies would already contain substantial dust with chemical compositions similar to those of modern galaxies. No one predicts that the dust production timescale would need to be compressed in the same way that the timescales for stellar formation and chemical enrichment need to be compressed. Absolutely no one anticipates the way the early dust observations have become another concrete example of how the standard models of the early universe need substantial refinement. Walk with me through what this implies for the broader picture of cosmic chemistry. The dust in the first galaxies represents a substantial fraction of the heavy elements that the first generations of stars produced. The dust is not just incidental matter. It is the form in which much of the cosmic carbon and silicon and other heavy elements existed in the early universe. The chemistry of the first galaxies, including their dust budgets, encodes the specific patterns of element production by the first stellar generations. The empirical detection of substantial dust in the first galaxies has prompted substantial theoretical work to identify the dominant production mechanisms. The leading candidates include rapid dust production by population 3 supernovae and dust production in the late stages of evolution of specific stellar populations. Whether either of these mechanisms can actually operate efficiently enough to produce the observed dust masses is an active question. The implications for how we observe the first galaxies are also substantial. Dust absorbs visible and ultraviolet light and re-emits it as infrared radiation. The most distant galaxies observed through the dust they contain appear dimmer in the optical and brighter in the infrared than they would in the absence of dust. The James Webb observations are specifically tuned to the infrared range, where the dust-affected radiation is most prominent. The first galaxies are, in this sense, particularly amenable to study with James Webb precisely because of their dust. Hold this image. The dust hidden inside the first galaxies is not a small effect. It is a substantial component of the interstellar medium of those galaxies, with masses comparable to those of much more mature systems and chemical compositions similar to those of modern galactic dust. The dust affects how we observe the first galaxies. The dust encodes the chemistry of the first stellar generations. The dust connects the various puzzles of the cosmic dawn era into a single coherent story of how the early universe became chemically and physically complex. The takeaway is that the early dust is one of the more concrete examples of how the standard cosmological picture needs revision. The first galaxies were not the simple, dust-free systems that the textbook predicted. They were already chemically and physically rich systems with substantial dust budgets that the standard models cannot easily produce. The implications extend across multiple aspects of early universe cosmology and represent one of the active areas of current research. The fifth thing hidden inside the first galaxies is, in some ways, the most important of all. It is the dark matter halo within which every galaxy, including the first ones, is embedded. Tonight, we're going to walk into the dark matter halos of the first galaxies because the James Webb observations are providing the first detailed constraints on the dark matter distribution at the cosmic dawn, with implications for what dark matter actually is. The basic picture is this: every galaxy in the modern universe is embedded in a much larger halo of dark matter, which dominates the gravitational dynamics of the system. The dark matter halo of the Milky Way, for example, contains approximately 10 times the mass of the visible stars and gas in our galaxy. The halo extends out to distances roughly 10 times the radius of the visible disk, with the dark matter providing the gravitational pull that keeps the outer stars and gas in their orbits. The same general picture applies to essentially every large galaxy that has been studied. The first galaxies, like all galaxies, must have formed within dark matter halos. The standard cosmological model predicts that the first dark matter halos massive enough to host galaxies began to assemble through gravitational collapse, perhaps 50 to 100 million years after the Big Bang. The halos grew through the gradual infall of dark matter from the surrounding cosmic web, with smaller halos merging to form larger ones over time. By the cosmic times at which the first galaxies are observed, perhaps 200 to 400 million years after the Big Bang, the host halos had grown to masses of perhaps 100 million to a billion solar masses. What follows from this is that the specific properties of these early dark matter halos depend sensitively on what dark matter actually is. Different candidate dark matter models predict different halo structures, different halo formation timescales, and different halo abundances at the cosmic dawn era. The James Webb observations of the first galaxies are, in this sense, providing empirical constraints on the dark matter physics that operated in the early universe. The standard cold dark matter model assumes that dark matter is composed of particles that interact only through gravity and are sufficiently massive that they were essentially non-relativistic at the relevant cosmic epochs. The cold dark matter model produces a specific prediction for the mass function of dark matter halos at any given cosmic time. The lowest mass halos are the most abundant, with the abundance decreasing rapidly toward higher halo masses. The first dark matter halos massive enough to host galaxies in the cold dark matter model formed at specific cosmic times that depend on the cosmological parameters. Now, let's begin with the alternative dark matter models predict different halo properties. Warm dark matter, which posits that dark matter particles are slightly less massive and were marginally relativistic at early cosmic times, suppresses the formation of the smallest halos and delays the formation of the first galaxies. Self-interacting dark matter, which posits that dark matter particles can scatter off each other in ways that produce observable consequences, modifies the internal structure of halos without strongly affecting their abundance. Fuzzy dark matter, composed of ultra-light bosonic particles, produces halos with specific quantum mechanical structures that differ from the cold, dark matter predictions at small scales. Pattern interrupt. The James Webb observations of the first galaxies are providing data that can distinguish between these alternatives in specific ways. The number density of galaxies at the highest redshifts, the masses of the galaxies, the structure of their stellar populations, and the relationships between galaxy properties and host halo properties all encode information about the dark matter halo distribution. The data, while not yet definitive, is beginning to constrain the parameter space of the alternative dark matter models. The most striking specific result has involved the abundance of galaxies at very high redshift. The cold, dark matter model, combined with the standard models of galaxy formation, predicts a specific number of bright galaxies at each redshift. The James Webb observations consistently find more bright galaxies at high redshift than these predictions allow. The excess is not enormous, but it is consistent across multiple surveys and at multiple redshifts. The pattern is real. The interpretation of this excess is still being worked out. Several possibilities have been proposed. One possibility is that the cold, dark matter model is correct, but the standard galaxy formation models need revision, with the first galaxies being more efficient at converting their available baryonic matter into stars than the standard models predicted. Another possibility is that the cold, dark matter model itself needs modification, with the abundance of dark matter halos at the cosmic dawn being slightly higher than the standard predictions. A third possibility involves modifications to the inflation models that set the initial conditions for cosmic structure formation, with the primordial fluctuations being slightly larger or differently shaped than the standard inflationary predictions assume. What this means is that none of these possibilities has been definitively confirmed. The James Webb data is consistent with several different interpretations. Distinguishing between them will require additional observations and additional theoretical work. The next several years of high redshift astronomy may produce substantial progress on this question. Walk with me through what this implies for the broader picture of cosmic structure. The dark matter halos that contain the first galaxies are, in a sense, the framework within which everything else happens. The population 3 stars form in dark matter potential wells. The supermassive black hole seeds form in the densest regions of these potential wells. The first heavy elements are scattered through the gas that fills the halos. The dust accumulates in the cold cores of those halos. Everything we have walked through tonight, the first stars and the black hole seeds and the chemistry and the dust, exists within and depends on the dark matter halos that the James Webb data is now constraining. No one expects, on first thinking about cosmic dark matter, that observations of distant galaxies could provide such direct constraints on the fundamental nature of dark matter itself. No one predicts that the question of what dark matter is would, in part, be answered by counting how many galaxies appear at specific cosmic times. Absolutely no one anticipates the way the cosmic dawn observations have become a probe of fundamental physics rather than just an inventory of early galaxies. The implications for the broader picture of cosmic structure formation are substantial. If the cold, dark matter model is correct, then the standard picture of cosmic structure formation works in broad outline, with the early galaxy data requiring only specific refinements to the baryonic physics of galaxy formation. If one of the alternative dark matter models is correct, then the entire picture of cosmic structure formation needs more substantial revision, with implications that extend from the first galaxies all the way to the present-day cosmic web. Hold this image. The dark matter halos that contain the first galaxies are, in this sense, the deepest layer of what is hidden inside them. The halos are not directly observable. They are inferred from the dynamics of the visible matter within them. The James Webb observations are providing detailed constraints on the visible matter at the cosmic dawn era, with the constraints implying specific properties for the dark matter halos. The chain of inference is long but rigorous. The dark matter halos are there. Their properties are being constrained. The constraints are beginning to distinguish between different candidate models of fundamental dark matter physics. Tonight, we're going to walk through the specific theoretical work on dark matter halos at the cosmic dawn era, because the simulations are one of the more sophisticated areas of computational cosmology, and the implications for understanding what is hidden inside the first galaxies are substantial. The basic challenge of cosmological simulation is to follow the gravitational evolution of dark matter from the very early universe through to the formation of galaxies. The dark matter starts out as a nearly uniform distribution with very small density fluctuations, encoded in the cosmic microwave background. The fluctuations grow under gravity over cosmic time, producing the network of halos and filaments that characterize the modern dark matter distribution. The galaxies form within the dark matter halos through the infall of baryonic gas and the subsequent collapse of that gas into stars. The numerical simulations that follow this process are computationally demanding. They require resolving structures across a wide range of scales, from the smallest dark matter halos that could host galaxies to the largest structures of the cosmic web. They require following the gravitational dynamics of large numbers of dark matter particles, plus the gas dynamics of the baryonic matter, plus the various baryonic processes including star formation, supernova feedback, and active galactic nucleus feedback. The simulations also require accurate cosmological initial conditions derived from the observed cosmic microwave background fluctuations. What surfaces from this is that the leading cosmological simulation programs have invested substantial effort in producing high-resolution simulations of the cosmic dawn era. The illustrious TNG simulations performed by a collaboration including Volker Springel at the Max Planck Institute for Astrophysics and Mark Vogelsberger at MIT follow cosmological volumes from very early times to the present day with detailed baryonic physics. The Eagle simulations performed by a European collaboration including JWST at Leiden University use somewhat different numerical techniques to address similar questions. The Fire simulations performed by a US collaboration including Philip Hopkins at Caltech focus on small cosmological volumes with very high resolution and detailed feedback physics. Pattern interrupt. Each of these simulation programs has produced specific predictions for the properties of galaxies in the cosmic dawn era. The predictions can be compared directly with the James Webb observations. The comparisons have produced some important results. The predictions for the number density of bright galaxies at very high redshift have been a central topic of comparison. The simulations predict specific luminosity functions describing how many galaxies of each brightness exist at each cosmic time. The James Webb observations measure the actual luminosity functions in the relevant redshift ranges. The two have been compared in considerable detail. The results have been mixed. The simulations broadly reproduce the general shape of the luminosity functions at intermediate redshifts, where the comparisons can be made carefully. At the highest redshifts, where James Webb is finding more bright galaxies than the standard predictions allowed, the simulations need modifications to match the data. The specific modifications vary across simulation programs, but the general direction is the same. The early universe was forming bright galaxies more efficiently than the standard simulations predicted. The predictions for the masses of dark matter halos hosting the first galaxies have also been a topic of comparison. The simulations predict specific relationships between halo mass and galaxy properties, including stellar mass, star formation rate, and metallicity. The James Webb observations measure these galaxy properties for the most distant galaxies. The comparison constrains the halo masses required to produce the observed galaxies, with implications for the broader question of what dark matter is. Step back, and you can see that the comparison has revealed specific tensions. The first galaxies, given the masses inferred from the comparison, are at the upper end of what the standard cold dark matter model can produce within the standard assumptions about baryonic physics. Either the baryonic physics needs revision, with the early galaxies being more efficient at converting their available gas into stars than the standard models predicted, or the dark matter physics needs revision, with the early halos being more massive or more abundant than the standard cold dark matter model predicts. The alternative dark matter models can, in principle, produce different predictions for the early galaxy properties. Warm dark matter, with its suppression of small-scale structure, would produce fewer and slightly later first galaxies than the cold dark matter model. The James Webb observations of substantial early galaxy populations argue against the most aggressive warm dark matter models. Fuzzy dark matter, with its specific quantum mechanical structure, produces galaxies with somewhat different internal properties than cold dark matter, with implications for the dynamics of the smallest galaxies. The current James Webb data does not yet have the resolution to distinguish between cold and fuzzy dark matter in detail. No one expects, on first thinking about cosmic structure formation, that the observations of the first galaxies could provide direct constraints on the nature of dark matter itself. No one predicts that the James Webb observations would so substantially contribute to the broader question of what dark matter actually is. Absolutely no one anticipates the way the cosmic dawn observations have become a probe of fundamental physics, in addition to being an inventory of early structure. Walk with me through one specific area of active work. The relationship between dark matter halo mass and stellar mass, called the stellar-to-halo mass relation, is one of the most important empirical regularities in galaxy formation. In the modern universe, the relation has been measured for galaxies across a wide range of masses. The relation in the cosmic dawn era is being measured by James Webb for the first time. The early results suggest that the stellar-to-halo mass relation may have been somewhat different in the cosmic dawn era than it is in the modern universe, with first galaxies producing slightly more stellar mass per unit halo mass than the modern relation predicts. The interpretation of this result is still being worked out. One possibility is that the baryonic physics of star formation was more efficient in the cosmic dawn era, because of the absence of the heavy elements and dust that regulate star formation in the modern universe. Another possibility involves the contributions of specific population 3 stellar populations that produce more luminosity per unit stellar mass than modern stellar populations. A third possibility involves modifications to the dark matter physics that change the relationship between halo mass and the gas content available for star formation. Hold this image. The dark matter halos hidden inside the first galaxies are providing direct empirical input to one of the deepest questions in modern physics, namely what dark matter actually is. The James Webb observations are constraining the dark matter halo properties of the cosmic dawn era. The constraints are still being interpreted. The implications extend across the broader picture of fundamental cosmology and may, over the coming years, contribute substantially to answering the dark matter question. What this leaves us with is that the fifth truth ties everything together. The dark matter halos are the framework. The population 3 stars are the first illuminating populations within that framework. The supermassive black hole seeds are the first compact objects to form at the centers. The chemistry and the dust are the products of the first generations of stellar evolution. The James Webb observations are providing direct empirical input on all of these components simultaneously. The first galaxies are, in this sense, the most empirically rich cosmic laboratory we have ever been able to access. Tonight, we're going to spend a careful pass on what the first galaxy observations imply for the broader picture of cosmic history, because the implications go beyond the specific empirical results and touch on how we should think about cosmic time and cosmic structure more generally. Before we get started, sit with the basic temporal scope of what is being revealed. The James Webb observations of the first galaxies are looking back in cosmic time by more than 13 billion years. The light we are detecting today was emitted when the cosmos was less than 3% of its current age. The galaxies we are seeing were, when their light was emitted, just beginning their assembly. By now, those same galaxies have evolved through more than 13 billion years of cosmic history, with their stellar populations growing, their black holes accreting, their chemical inventories building up, and their structures gradually approaching the configurations of modern galaxies. The galaxies that James Webb is observing in the cosmic dawn era are not, by any standard interpretation, the same galaxies that exist in the modern universe at those locations. They have evolved substantially over the intervening cosmic time. Some of them have grown into the massive elliptical galaxies and giant spiral galaxies that dominate the modern cosmic web. Some of them have been disrupted through mergers with other galaxies, with their stellar populations being incorporated into larger systems. Some of them have probably been consumed entirely by their growing supermassive black holes or by other gravitational processes. The point worth taking away is that the cosmic dawn observations are therefore providing a snapshot of cosmic history at a specific moment. The snapshot is one of the most important moments because it is the boundary between the dark ages of the cosmos and the structured universe we live in today. Whatever happened during the cosmic dawn era determined what kind of cosmos would emerge. The James Webb observations are giving us direct empirical access to this critical period. The implications for the cosmic history of ordinary matter are substantial. The atoms in your body, including the carbon in your cells and the iron in your blood, were forged in the cores of stars that lived and died long before the Sun and Earth existed. The first generations of these stars, the population 3 stars that we have discussed, produced the first heavy elements in the cosmos. Subsequent generations of stars inherited and recycled these elements, gradually building up the chemical inventory that eventually allowed for the formation of rocky planets and the development of biology. The chain of cosmic chemistry that leads to your existence began in the first galaxies. Take a slow breath here. The chain is direct and traceable. The carbon in the carbon dioxide you exhale was forged in the cores of massive stars and scattered by their supernovae. Some of that carbon was forged in the first generations of stars in the first galaxies. The oxygen you breathe was forged in similar processes in similar stars across cosmic time. The iron in your hemoglobin was forged in the highest temperature regions of the largest supernovae, including possibly some of the first supernovae in cosmic history. The atoms that constitute you are, in this sense, the products of an enormous cosmic chemical factory that has been operating for 13 billion years, with the first galaxies being the first manufacturers. The implications for cosmic structure are similarly direct. The galaxies we see today, including our Milky Way and Andromeda, and the more distant galaxies of the cosmic web, are the descendants of the first galaxies. The hierarchical merger process that builds up galactic structure over cosmic time has its origins in the assembly of the first dark matter halos and the first gas accretion events. The modern cosmic web, with its galaxies and clusters and filaments and voids, is a derived consequence of what happened in the cosmic dawn era. The James Webb observations are providing direct empirical input on these origins. The first galaxies, with their population 3 stars and their black hole seeds and their early chemistry and their early dust and their dark matter halos, are the precursors of everything we see in the modern cosmos. The empirical study of those precursors is, in this sense, the empirical study of the origins of cosmic structure as we know it. No one expects, on first thinking about the cosmic dawn era, that the observational study of such distant objects could be so directly informative about the origins of cosmic structure. No one predicts that the James Webb data would so substantially advance our understanding of the deep cosmic past. Absolutely no one anticipates the way the first galaxy observations have become one of the more empirically productive areas of modern cosmology. Expectation. Cosmic history is a smooth and uninterrupted process from the Big Bang to the present. Reality. Cosmic history contains distinct epochs with substantially different physical conditions, with the cosmic dawn era being one of the most important transitions and the first galaxies being one of the most important features of that transition. What becomes clear is that this is part of what makes the first galaxy observations so interesting. They are not just additional data points in a continuous record. They are direct empirical access to a transitional epoch that determined the subsequent character of the cosmos. The work of understanding the first galaxies is, in this sense, the work of understanding how the modern cosmic structure came into being. The cosmic web that surrounds the Milky Way today, with its hundreds of billions of galaxies arranged in filaments and clusters, has its origin in the first galaxies. The supermassive black holes that occupy the centers of large galaxies, including Sagittarius A star at the center of the Milky Way, have their origin in the seed black holes of the first galaxies. The chemical inventory that allows planets and biology to exist has its origin in the first generations of stellar nucleosynthesis. The cosmic dust that fills the modern interstellar medium has its origin in the dust production of the first galaxies. The dark matter halos that contain the modern galactic structure have their direct ancestors in the dark matter halos of the cosmic dawn era. Hold this image. The cosmos that contains you tonight is the direct descendant of the cosmos that the first galaxies inhabited. The connection is not poetic, it is empirical and traceable. The James Webb observations of the first galaxies are, in this sense, observations of your cosmic ancestors, looking back through more than 13 billion years of cosmic time to the moment when the conditions that eventually allowed your existence were being established. This is part of what makes the current moment in cosmology particularly interesting. We are alive at a time when the cosmic dawn era is being directly observed for the first time in human history. The implications are being worked out by the broader scientific community. The textbook chapter on cosmic dawn, written 10 or 20 years from now, will be substantially different from the chapter that was available before James Webb. We are part of the generation that is alive to witness this revision in real time. What this leaves us with is a clearer sense of why the first galaxies matter. They are not just curiosities of distant astronomy. They are direct empirical access to the cosmic origins of everything we now observe. The 5 things hidden inside them, the population-throwing stars, and the black hole seeds, and the chemistry, and the dust, and the dark matter halos, are the components from which the modern cosmos was eventually assembled. The James Webb observations are slowly revealing how that assembly began. The revelation is one of the more substantial scientific achievements of the current era. Tonight, we're going to address the 5 most common misconceptions about the first galaxy discoveries, because each one is widely repeated in popular discussion, and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that the James Webb observations have refuted the Big Bang. This claim has appeared in numerous popular contexts, often with elaborate alternative cosmologies attached. The technical reality is that the James Webb observations are fully consistent with the Big Bang model. The first galaxies are appearing at exactly the cosmic times where the Big Bang model predicts they should be observable. The cosmic microwave background, which is the primary direct evidence for the Big Bang, is unaffected by the new data. The Big Bang model is not in question. The standard galaxy formation models within the Big Bang framework are. No one expects, on first hearing the popular claim, that the gap between the headline and the technical situation could be quite this large. No one predicts that the most widely repeated interpretation of the first galaxy data would so substantially overstate the actual scientific situation. Absolutely no one anticipates the way the news cycle has compressed a complicated and ongoing scientific discussion into a single dramatic claim about cosmic origins. Before we get started on the second misconception, take a moment to acknowledge why the first one persists. The framing of the Big Bang being refuted is dramatic. It generates attention. The technical framing of accumulated tensions putting empirical pressure on specific models is less dramatic, but more accurate. Now, let's begin with the second misconception. The misconception is that the first galaxies prove the universe is much older than 13.8 billion years. The claim has appeared in various forms, sometimes with specific suggestions of much greater cosmic ages. The technical reality is that the age of the universe is determined primarily by the cosmic microwave background measurements, not by the first galaxy data. The CMB-based age of 13.8 billion years is robust and is not in question. The first galaxies appearing earlier than expected within that age does not change the age of the universe. It changes our understanding of how fast structure formed within that age. Notice that the popular framing of an older universe is a misreading of the data. The cosmic time of any specific first galaxy is determined by the redshift of the galaxy and the standard cosmological parameters. The standard parameters give a consistent age of the universe. The galaxies are appearing earlier than expected within that age. The age itself is not in question. The timeline of structure formation within the age is. The third misconception is that the James Webb observations show that something exotic must be present in the first galaxies. The claim sometimes appears with suggestions of dark stars, primordial black holes as dark matter, or other exotic phenomena being directly observed. The technical reality is more measured. The first galaxies contain ordinary baryonic matter, ordinary stars, ordinary black holes, ordinary chemistry, and ordinary dust, with the only thing being surprising being the timing of when these components appeared. The exotic explanations have not been confirmed and are not the leading interpretations among working cosmologists. Expectation: the first galaxy data has revealed exotic new physics. Reality: the first galaxy data has revealed that ordinary physical processes operated faster in the cosmic dawn era than the standard models assumed, with the specific reasons still being worked out. The fourth misconception is that the first galaxies show the universe has features that the standard models cannot accommodate at all. The claim sometimes appears as a more general suggestion that cosmology is fundamentally broken. The technical reality is that the first galaxy data is producing specific quantitative tensions with the standard models, which the theoretical community is actively incorporating into refined versions of those models. The tensions are real and significant. The models are not being abandoned. They are being refined in specific ways to accommodate the new data. No one predicts, on first thinking about modern cosmology, that the field would be in such an active state of refinement. No one expects that a single space telescope, launched only a few years ago, would so substantially reshape the empirical landscape. Absolutely no one anticipates the way the combined tensions, taken together, are pushing the field toward what may turn out to be one of its more consequential periods of theoretical development. Take a slow breath here. The fifth misconception is that the first galaxy observations will not change how cosmologists think about cosmic history. The claim sometimes appears in discussions that frame the new data as merely incremental progress. The technical reality is that the data is substantially reshaping our understanding of the cosmic dawn era. The textbook timeline has been compressed, the chemistry has been pushed earlier, the supermassive black holes have been pushed earlier, the dust has been pushed earlier. The combined picture of the cosmic dawn era will be substantially different in the textbooks of 2035 than it was in the textbooks of 2015. The change is not incremental, it is substantial. What this picture tells us is that this is part of why the current moment in cosmology is interesting. The first galaxy observations are producing genuine empirical reshaping of how we understand the deep cosmic past. The reshaping is not happening because cosmology is broken. The reshaping is happening because the new instruments are providing direct empirical access to a cosmic epoch that was previously only theoretical. The empirical access is producing surprises. The surprises are being incorporated into refined models. The work continues. Hold this image. 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of the actual discoveries. The discoveries are genuinely significant. The discoveries are genuinely changing cosmology. But the discoveries are not what the dramatic versions suggest. The technical situation is more measured and, in its own way, more interesting than the popular versions allow. What this leaves us with is a clearer view of what the first galaxy observations actually mean and what they do not mean. They are reshaping our understanding of cosmic dawn. They are not refuting the Big Bang. They are not making the universe older. They are not revealing exotic new physics. They are not making cosmology fundamentally broken. They are providing direct empirical access to a critical cosmic epoch that was previously only theoretical, with substantial implications for the broader picture of how the cosmic structure that contains us came into being. For the next stretch, we spend a careful pass on what comes next in the empirical study of the first galaxies, because the directions of current and planned work are worth knowing, and the next decade promises substantial additional progress. Now, let's begin with the first major development to expect. James Webb will continue to observe the cosmic dawn era for at least another decade. The observatory's mission lifetime is currently expected to extend to at least the early 2030s, with conservative engineering estimates suggesting a working lifetime of about 10 years from launch. The actual lifetime will depend on the available cryogenic propellant and the reliability of the various instruments. During its remaining operational time, James Webb will continue to push the high redshift frontier deeper, with new galaxies at progressively higher redshifts being discovered and confirmed. The continuing James Webb observations will refine our understanding of the first galaxies in several specific ways. The number density measurements at the highest redshifts will become more precise as the total survey area increases. The spectroscopy of individual galaxies will improve as deeper observations become available for the most interesting targets. The detection of population 3 stellar signatures, including the helium-2 emission line, may finally cross the threshold from suggestive to definitive. What emerges from this is that the second major development involves the Roman Space Telescope, also known as the Nancy Grace Roman Space Telescope, which is scheduled for launch in 2027 by NASA. Roman will have a field of view approximately 100 times larger than the James Webb field of view, with similar sensitivity in the relevant infrared bands. The combination will allow systematic wide-area surveys of the first galaxies, with statistical samples that will dwarf the current James Webb samples. Roman will be particularly valuable for measuring the number density of bright first galaxies. The current James Webb measurements are based on relatively small fields of view, which makes the statistic susceptible to cosmic variance, the random fluctuations in galaxy counts from one patch of sky to another. Roman, with its much larger field of view, will reduce the cosmic variance substantially and provide much more reliable statistical measurements. Slow down here. The third major development involves the Euclid satellite, launched in 2023 by the European Space Agency. Euclid is conducting a wide-area survey of the sky in the near-infrared, with capabilities complementary to both James Webb and Roman. The Euclid data will provide additional statistical samples of high redshift galaxies and will contribute to the broader empirical picture of the cosmic dawn era. The combination of James Webb, Roman, and Euclid will, by the early 2030s, provide a comprehensive empirical map of the cosmic dawn era at multiple scales. The combined data will substantially advance our understanding of when and how the first galaxies formed, what they contained, and how they fit into the broader picture of cosmic structure. The fourth major development involves ground-based facilities. The extremely large telescope, currently under construction in Chile by the European Southern Observatory, will have a 39-meter primary mirror that will provide extraordinary sensitivity for high redshift spectroscopy. The Giant Magellan Telescope and the 30-meter telescope, also under construction, will provide complementary capabilities. The combination of these next-generation ground-based telescopes will substantially advance the spectroscopic characterization of the first galaxies, with the next decade seeing the most detailed observational program ever conducted on these distant objects. The takeaway is that the fifth major development involves the theoretical response. The cosmology community is actively working on revised models of galaxy formation that can accommodate the James Webb data. New simulations are being run with different assumptions about population 3 star properties, baryonic feedback mechanisms, dark matter, halo physics, and various other relevant inputs. The simulations are computationally expensive, but are increasingly producing predictions that can be compared directly with the new observations. Over the next several years, the theoretical landscape will likely undergo substantial revision in response to the new empirical input. No one expects, on first thinking about the future of cosmic dawn observations, that the next decade would offer such a substantial expansion of empirical and theoretical capability. No one predicts that multiple major facilities would be operating simultaneously on the question of the first galaxies. Absolutely no one anticipates the way the next phase of cosmic dawn research may turn out to be one of the more productive in the history of the field. Walk with me through what this implies for the broader picture. The 5 things hidden inside the first galaxies that we have walked through tonight are real empirical findings. The next decade of observation and theoretical work will, with substantial probability, sharpen our understanding of each of them. The sharpening may come quickly or slowly, but the direction of progress is clear. The combination of new observational data and new theoretical understanding will, over the coming decade, substantially refine our picture of what the first galaxies actually contained and how they fit into the broader cosmic narrative. There is, in this picture, a particular kind of intellectual optimism that is appropriate to the contemporary situation. The first galaxy observations have provided extraordinary new empirical input. The investigations of the implications are active and well-funded. The next phase of investigation is being prepared with substantial resources. The trajectory of progress points toward continued advancement of our understanding over the next several decades. Hold this image. The next decade of cosmic dawn research will involve substantial new observational programs, substantial new theoretical work, and substantial new computational capabilities. The 5 things we have walked through tonight will be tested more carefully than they have been to date. Some of the current puzzles will probably be partially resolved. Others may persist for further generations. The first galaxies will continue to reveal themselves slowly and gently through the patient work of the broader scientific community. What follows from this is that this is part of why the current moment in cosmic dawn research is particularly interesting. The combination of the early empirical surprises from James Webb, the substantial expansion of upcoming observational capability, and the active engagement of large theoretical communities has produced a particularly productive period in the field. The next major advances, whatever they turn out to be, will likely emerge from this combination of ingredients. We are alive at a moment when the empirical study of the first galaxies is approaching what may turn out to be one of its more dramatic phases. What this leaves us with is a sense of why the current moment matters. We are alive during one of the more capable phases of cosmic dawn research in its history. The work continues. The instruments improve. The theoretical understanding deepens. The hidden contents of the first galaxies are being probed from multiple directions simultaneously. The first galaxies will continue to be studied with increasing care, and the implications for the broader picture of cosmic structure will continue to be worked out by the active engagement of the scientific community over the next several decades. For the rest of the night, sit with the 5 things hidden inside the first galaxies. Population 3 stars, the very first generation of stars in cosmic history whose direct signatures remain just out of reach, but whose chemical fingerprints we can read in the galaxies they once inhabited. Supermassive black hole seeds, present at the centers of the first galaxies in masses that the standard formation mechanisms struggle to produce in the available cosmic time. The first heavy elements scattered into the interstellar medium of the first galaxies by the first supernovae, present in quantities that the textbook timeline did not anticipate. Cosmic dust, accumulated in the interstellar medium of the first galaxies through mechanisms that the standard models had assigned to later epochs, and dark matter halos, the framework within which everything else is happening, whose properties are now being constrained by the James Webb observations in ways that have implications for the fundamental nature of dark matter itself. 5 hidden components, 5 distinct empirical surprises, 5 different ways in which the first galaxies are turning out to be more empirically rich than the standard models had prepared us for. Picture, for a moment, what one of the first galaxies actually looks like. The James Webb image shows a small, faint, point-like, or barely resolved source against the dark background of the deep field. To the eye, the galaxy appears as little more than a single pixel or 2 of light in an enormous mosaic of similar tiny sources. But the spectroscopy reveals what is inside. The light contains the spectral signatures of carbon, nitrogen, oxygen, and other heavy elements. The brightness, when compared to the standard models, implies a higher star formation rate than expected. The emission lines, when interpreted carefully, reveal the presence of an active galactic nucleus powered by a supermassive black hole. The continuum spectrum, when analyzed for reddening, implies substantial cosmic dust. The total brightness across all the wavelengths, when compared to the expected luminosity per unit halo mass, implies specific properties for the dark matter halo within which the galaxy sits. All of this is encoded in a single faint smudge of infrared light captured by a telescope orbiting 1 million miles from Earth, after 13 billion years of cosmic travel. The first galaxies are, in this sense, both extraordinarily distant and extraordinarily informative. The light from them carries the deep history of how the cosmic structure that contains you came into being. Slowly, the camera in your imagination drifts outward. It leaves the room where you are sitting. It rises above the building, above the city, above the planet. It travels outward through the solar system, the galaxy, the local group, the cosmic web of nearby galaxies. It pushes further, past the more distant galaxies that Hubble can resolve, into the redshift range where James Webb is now mapping the first galaxies. The first galaxies appear in the field, scattered across the deep infrared sky, each one a faint smudge of light, carrying the signatures of the components we have walked through tonight. The camera continues outward, in time as well as in space. It approaches the cosmic dawn era. The first galaxies are forming in the field, with their hidden components just beginning to assemble. The population 3 stars are igniting in the densest gas clouds. The supermassive black hole seeds are forming through direct collapse or through other mechanisms in the deepest gravitational wells. The first supernovae are scattering their chemical products into the surrounding gas. The first dust grains are condensing in the cooling ejector. The dark matter halos are growing through gravitational accretion and merging, providing the framework for everything else. The camera turns around and begins the long drift back, past the cosmic dawn era, past the first galaxies, past the cosmic web of more mature galaxies, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room, on this night, in this particular body, is the version that is alive at the moment when the first galaxies are becoming directly observable for the first time in human history. The cosmos is the cosmos. The James Webb observations are the James Webb observations. The implications for what is hidden inside the first galaxies are still being worked out by the broader cosmology community. What this means for how you experience the cosmos tonight is subtle. The night sky outside your window contains the same stars as it did before James Webb launched. The same galaxies are out there. The cosmic structures are exactly where they were. What has changed is the layered understanding of how those structures came into being. The first galaxies, which used to be theoretical placeholders, are now empirically rich systems whose internal components are being mapped. The deep early universe is becoming, for the first time in human history, directly accessible to careful empirical study. The cosmos has, in this sense, given you a particular cosmic moment. You are alive at the start of one of the more significant observational programs in the history of cosmology. The first galaxies are being mapped beat by beat as the James Webb data accumulates. The implications are being worked out paper by paper as the theoretical community grapples with the new empirical input. The textbook chapter on cosmic dawn in 2035 will be substantially different from the chapter that was written in 2015. You are alive to witness this revision in real time. There is no need to hold all of this in your mind. The 5 things will keep their shape whether you remember the details or not. The James Webb observations will continue to accumulate. The implications will continue to be worked out. The cosmos that contains your sleeping body is the same cosmos that contains the first galaxies, with all their hidden components, drifting at distances that no human will ever directly visit, but whose internal physics we are now beginning to map with extraordinary care. Sleep can come whenever it wants now. The story has done its work. The first galaxies are out there in the cosmic dawn with their population 3 stars and their black hole seeds and their first heavy elements and their early dust and their dark matter halos. The cosmos is what it is. The work of mapping its earliest structures continues. You are part of the generation that is alive while this is happening. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.